So this is a simple question in the sense that there is not much involved, not many forces, just a single force that is involved. So curve frame of shown cross section is loaded as follows. Um, Determine the stresses at A and B. So A and B is basically, if it's not clear, this is point A and this is point B. So it's basically saying what are the stresses on the inner and the outer part of the beam, kind of, and determine the maximum tangential stress. So in the sense, the maximum tangential stress, you are trying to figure out the tangential stress at A and B, right? The radial stress, there is no radial stress at A and B. There won't be a tangential stress there. So the cross section is a little involved. It's like this T-shaped thing. So it's like what they're basically saying is that B, right? So it's going to be something like this, and that T is rotated all around. That is how the cross section is, and you have to basically use what you have derived so far in class to get what this is. So when you solve chord beam problem, so this problem is technically something like this, right? So there is this C-shaped beam. There is a force P, and there would be an equal and opposite reaction at the other end by the ground. There's a force P here as well. And you have, yes, and you, and for problems like this, right, what you have to use generally is you have to find out where the neutral axis is. You have to find out where the centroidal axis is and stuff like that. The formula that you used in class, right? So something like all of this. So for this, you need to know what the neutral axis Rn is. For E, you need to know what Rn is, what the centroidal axis, I don't know what the centroidal axis is called. Is it R bar? I'm not really, let's see, what the centroidal axis is. Oh, it's just called capital R. Okay, awesome. Uh, okay, so you have, for E, you need to know Rn and R. N, M, all of these are, depending on where you make the cut, you figure out what the axial force at that point is, what the moment at that point is. So all of this, you put it in the formula and you should get your sigma theta theta directly. So let's look at all of these points, right? So first, N, M, I'll go to the forces later. Let's look at the geometric properties first. A is the entire area of cross section for that T, right? So let's look at that T. So what is that T? 4630. So just copy this. It'll be easier. Okay. So what is the area of the cross section? So what I'm going to do here is I'm going to divide this T into two rectangles. So there is this horizontal rectangle and there is this vertical rectangle. Why I'm doing this? Because I want to find out what the centroid of this is, right? Eventually. So if I want to find out what the centroid of that is, then I cannot find a centroid of T, but I know how to find a centroid of a rectangle. So I divide it into two separate rectangles. Say this is rectangle 1 and then this is rectangle 2. Okay. So area A is going to be simple. It's going to be A1 plus A2. And that is what? This is 40, right? If this entire thing is 46, this part is 6, then this is 40. So 40 into 6 is 240. I'm assuming, what is the units? Let's say the units. I think the units are all going to be in millimeter. So into 10 raised to minus 6 meters square. Plus the area of this is 30 into 6. So it's 180 into 10 raised to minus 6 meters square. So I know what the area is, right? So capital A is known. So let's look at what the centroid of this thing is, right? So if this is the cross section. Say I define an axis something like this, right? So an L, like a centroid axis. So I try to put, say this is a Z centroid axis. And what I do is that I know what the centroid of the first rectangle is going to be, right? So it's going to be at somewhere at the center. So it's going to be Z equals 20. So it's going to be at the center, and this z-axis goes through the very center of this. So I don't have to worry about, the vertical displacement of the centroid because it's at the center. So this goes through z equals 20. And you know that this also is going to lie on the z-axis, right? At the centroid of this part of the the rectangle. So this is z1 equals 20 and z2 would equal, this is 40 and this is 3, half of 6 is 43. So I want to find out what is the z for the entire t-shaped cross section. So how do I do that? Let's say the centroid is somewhere here, for example, at z bar. Then I say z bar equals a1 z1 plus a2 z2 upon a1 plus a2. So that is how I find out z bar. This is how you find, yeah, sure. So because the way I have defined the axis for my calculation of z position of z bar, both the centroids of the two parts lie on that axis. So it's so I know that if both the centroids of the two parts lie on that axis, then the centroid of the entire thing is going to lie on that axis as well. So it's going to be that. That is the way I define it. So it just makes the calculation easy. Well, if they are not on the same axis, then you would have to, look at the x as well as the y thing. So you'll have to do probably a1 x1 plus a2 x2, and then you'll get x comma y, and then you say, so that is where the centroid is positioned. You still haven't, you have to figure out what is the radius of the centroidal axis. This does not account into that yet. So this does not even look at the bigger picture. This just looks at the cross section. So once you find out what that point x comma y is, then you can just figure out what the radius is. So distance of that point from the center of the big beam, for example. So very similar way I'm going to do this, but I'll show you. So right now, since it's easy, I can just define one axis and get my work done. If it's not possible that they are on the same axis, then what you have to basically do is, get your x and y coordinates. So you get x bar and y bar. So you can define where the point is on the plane. That's it. So this is how I do it. Let's see if I have the numbers for this. Makes life easier. Um, haven't had to solve this before. Okay, I think I have. So it's 29.86 millimeters. That's good. So this is 29.86 millimeters. So what this says is that from this point to this point, the distance is 29.86 millimeters. So now if you look at the big beam, right? If you look at this beam, you know the inner radius. So you know the distance, the inner radius of this point here is Ri. And you know that the radius of any point on this side is R naught. If you look at the beam and the cross section. So anything, so the radius of the centroid, which is here at 29.86 millimeters. So the radius of the centroid capital R is going to simply be Ri plus 29.86 millimeters. Is that part clear? How I got capital R? So you know where the point is on the cross section. You know what the distance is from the inner radius and the outer radius. So you can figure out what the distance is from the center. So the distance of this point from the center is Ri. So the distance from this point from the center is Ri plus 29.86 millimeters. That's it. So that is how I calculate R. So you first look at the cross section, you figure out where the centroid is, just looking at the cross section itself. And then you figure out what the radius is with respect to the rest of the beam. So that is how I find capital R. So that's step one. I found capital R, and I still need to find Rn, right? I haven't found the neutral axis. So how do you get the neutral axis on this? So there is the way to get the neutral axis is little similar to how you get the what do you say? You get the centroidal axis. So let's look at that. So this is your bar. So the way you get the neutral axis is there is a formula. Let me copy that formula from the slide so you know how it looks like. Um, So the way you get the neutral axis is by looking at this. Uh, so you solve this equation, which is basically comes from, if you go through the lectures, will come from where the hoop stress doesn't, what like, it basically comes from the fact the where no hoop stress exists in absence of n. So if there is no n, like there is no axial force, there'll be no hoop stress. So that is where the neutral axis comes from. So it's, if you look at the derivation of it, you'll find that there is this formula which gives you what the neutral axis location is. And that is the exact formula that we are going to use to solve for the neutral axis. And that is this formula, which basically says that R equals integral dA upon integral dA by R. And that is easy. The integration would have been easy if it was, a circle, for example. So you know what integral dA is. But now it is like two separate blocks. And with two, the r's are also separate. So you don't really know where, what integral dA by R is, for example. So what I'm going to do is I'm going to replace again separate it into two parts. So I know what the numerator is. That is simple. It's A1 plus A2. And now I have to find what the denominator is going to be, right? So if you look at the first part, how do I erase this? Mhm. Yeah, Rn. This is Rn. The radius of the neutral axis. So this is the center, right? So from here, this is the center O, this is A, this is B. So you know this is Ri. This is some distance R, for example. And then this outwardly, this is R naught here. If this is the R axis, for example. So you know the radii from A to B. So what you do is you take a small patch of dA here, say here at radius R, and you say this is dA by R, and you integrate it over the entire cross section. That is how you get the denominator. So what we are going to do is we are going to make it slightly easier by separating into two sections. So you get this and you get this. So what is the dA for this? The dA is going to be this thickness into dr, right? So this is dr. So small, we are taking a small small part of the cross section from radius r to radius r plus dr. So there's going to be this small dr, and this thickness is the same. So at any point on this radius from point A to this part here, the intersection of the two rectangles, the thickness is going to be the same. So it's T, this thickness T into dr. So area, so the first part is going to be integral T dr upon R. And you know that R goes from this Ri to Ri plus 40 millimeters. And this T is probably 6 millimeters as far as I remember. And that is for the first rectangle. So you are doing the same thing that's there in the denominator. You are integrating dA over R. And R varies from Ri to this part, which is Ri plus 40 millimeters. And you do similarly, you do it for the second part. You do Ri plus 40 millimeters now to R naught. So from this R here to this R, you take a small area. So you take something like this. I'm going to delete this part. Okay, and now I'm taking a small area again, where this is dr, and this is 30 millimeters as far as I remember. I don't know the values are correct, but something like that. So the small dA would be 30 dr, 30 millimeters into dr upon r, where r varies now from Ri plus 40 millimeters to the outer radius Ru. So the the denominator would be dA by r for the first rectangle plus dA by r for the second rectangle. Is it clear how I get the radius of the neutral axis? By doing this integration. Sorry? It could be R0 minus 6. It has the same values. They would be the same values. So basically you have to just figure out what is the initial radius and the final radius. Just whatever that is. So now you have your Rn. So you had your R and you had your Rn. So let's look at the values. Okay. Yeah. So capital R is 132.19. This is capital Rn is 119. And capital Rn is that, and capital R is 29.86 plus the initial radius Ri. So it's 133.86. So something like this. So this is the cross section. So millimeter. Okay. What is Ri? Uh, R naught is given. Ri is not given. So R naught is 150 millimeters. So you know what Ri is because you just do Ri is 150 minus 46, right? So you know what Ri is. So that is so you know what Ri and R naught are. So I'm not into that. So it's 150. So I think somewhere here is your centroidal axis and somewhere here is your neutral axis, something like that. So it's a radius, right? So it's along the beam, for example. They are the points are it's going to be something like this. So there's going to be your neutral axis and your centroidal axis, something like that. You take the cross section, you find out what the point or the radius is, and this is how it's going to look in your final diagram. So you have both of this. So the next step, coming back to what we are actually started out with is this formula, right? So you know A, you know Rn. What is E? E is basically R minus Rn, or is it the other way around? Yeah, R minus Rn, and that is 1.67 millimeters. So now you have everything. You have A, Rn, E, all of that. So now the only thing remaining is to find out what the axial force and the moments are. So what you want to do is you have to find out what the stresses are in this part, right? You want to find out the stress at A and B. So we are going to look at what the axial force and the moment are at A and B. So let's look at this. So this is the beam. Okay, and I make a cut. Oh, wow. So I make a cut here at A and B. So I open a surface. Okay. So something like this. See? So there is N like this. There is M like this. So how do I find out what N, M, and P are? Is that what N and M are in terms of P and the material? The geometric properties. Is that N is simple, right? N is simply minus P, force balance. So there is nothing in there. What is M? M is, you can basically, the way you can do it is you can take a small part here you can find out what the movement of that is. You're trying to do a movement balance in this, right? So there is no movement here because of n, for example, but there'll be a movement because of p. So what you do is you do p into capital R, the centroidal axis. Why you do that is because if you do that integration, right? So p into the small movement there and so on. You'll do this, you take this R, you find out what the movement is, you take this R, you find out what the movement is. Eventually, if you do that integration, it's going to be, you can get PR, which is R is the centroidal axis. So you can replace this movement, capital M, by, is the direction correct? This is going to be in this direction. No, I think it's negative, minus PR. Is this part, this part, is this clear or is this still confusing? That that is like the, the way you can calculate let me try to see if I can explain that a little better. R is the centroidal axis. So is this like bypassing the integration? It's bypassing the integration. But if it works like integration, you will probably end up with the same thing. Okay, it's R instead of, this is the centroidal axis. This capital R is the centroidal axis. So it's basically a distance of the centroid. Capital R is the distance of the centroid from the center. This is where the P is acting, right? So if I take P, for example, let's try to do this, right? Let me see if I can help you do this. So how would I do this? If I take this distance, right? So this is some distance. Let's see. How does the cross section look? It's like that. Okay. So the cross section is something like this, right? Let's see if we can derive this so that you know where it came from. The cross section is something like this. This is the cross section. So now what if I want to find out the moment of P at this point? So moment of P at this point is I take this distance, right? So what is this distance? Remember we used this Z to find what the centroid was? So we took the Z axis, right, to find out what the centroid was. So I'll still use the same Z axis. So it's Z plus Ri. So it's P into Ri plus Z. Is going to be that small movement because of the P force. Is that correct? So that's Tm. So this is the entire movement here was M. So what I'm going to do is going to do a small dm and then I'm going to add it across the entire thing. So first of all, is it clear where the negative sign is coming from so that I don't have to explain from? If you just do a force balance, we look at that, the movement in P is in this direction. So M, so you get the same thing. We do a movement balance, right? So it's M plus P into R, for example, equals 0. So M is minus PR. That is where the movement comes from. So if you look at this, let's put it here. So we have a small movement because of P. So it's not dm. Let's take a different M. So we have M plus MP equals 0. The movement because of P. So MP is minus M or the other way around. That is how it works. So what we are trying to do is we are finding MP by taking small movements, which is P, into the distance to that particular point, which is P into, it is Ri plus Z. Okay. So the way you find the moment is that for that particular area here, the moment is this, right? So you basically do for that small area, the moment is that upon the total area. And that is how you do it. For that small area, the moment is this. So what is the total moment? It will be like a mean. It's like taking the mean of the moments, right? So it's like you are adding up the moments. And that is basically what you did in the centroidal calculation. Is that part clear? Kind of clear. I'll see if I can, brush this up a little, but as far as now, I just want to, yes, go ahead. Confused by the sign convention. So which part exactly? So let's see. So the way I do n and m in this is n and this is m. So why I do this is sorry, my bad. Is this m? M is in the other way. Did I use it in the calculations correctly or did I use it the other way? Oh, okay.
Yeah. So that way it's opposite of.
So there is P, then there is M. So then M must be PR, not minus PR. Is that correct or are we still?
Right, if you take them down.
Correct. So it'll be M plus PR equals 0, or it'll be M minus PR equals 0. If you look at this, if you do a moment balance in say this direction, then it's M minus PR equals 0. So this is actually plus PR. That's what this is. If I use this side of M, then it's going to be something like this. Is that correct? So how do you define what the sign of M is for your formula? Is I think the way it was explained in class, if it's compression on the inside and extension on the outside, that is the way you define M. So it's bending inside. Correct. So the way I look at it is with my sign convention, which I'm going to tell you. I hope that doesn't confuse you. If it's confusing you, just ignore it. Is that, this is how you look at theta, right? The theta axis. This is a polar coordinate system, right? We have done sign convention so far in the Cartesian coordinate system. But this is the polar coordinate system. This is r cap and this is theta cap, the normal vector. And outside it's going to be z cap. Is that clear? So what is the normal for this side? It's in positive theta cap. This edge, the normal is in the positive theta cap. So that is how the forces come, the signs come. So if you look at n, it's in the positive direction. If you look at m, it's in the positive z direction. That is how, very similar to how we look at the Cartesian coordinate sign system. I'm going to keep it there for a second so you can figure out. The normal and the forces are in the same direction. Is this part clear? Yeah, m is coming out of the plane, right? So if you look at r theta, m is in the positive z direction. The normal is in the positive theta direction. P cross r, yeah. No, if you don't look at P, don't look at P. Just look at N and M, for example, and look at the Cartesian coordinate system. Oh, sorry, the polar coordinate system. So the similar way to we did sign convention, right? If the normal is in the positive direction, forces in the positive direction are the correct sign convention. So if you look at that, the normal is in the theta direction. So capital N is positive in the positive theta direction, and M is positive in the positive z direction. So what is the positive z direction from r to theta? So it's outside the plane. That is basically
You have outside the plane.
correct.
Then and
So
in the
correct. No. So yeah. No, so what do you think the direction of MP is? Is inside the plane, right? Correct. So you just know that M plus MP. Give me a second.
Oh, because they're going opposite directions, you could be going opposite.
Correct. Let's look at what it's going to be. Okay. So let's see MP is PR, right? So you know M. Just look at the force balance. How would you do force balance? Is you add the forces in the same direction. So you add the moments in the same direction. So there is M like this, which is outside the plane. Then there is, if you look at just moments outside the plane, then MP is going inside the plane. So it should be negative MP. So it's M minus MP equals 0. So M equals MP. And MP is PR from what we calculate. I did do a sign mistake while showing you the first time. So I'm hoping there is no confusion. Or if there is any, we can go over this again. The way it has been done in class is perfect. So if M is curving the beam inside, then that is the way it goes. So if you look at the M, it's trying to curve the beam inside, right? It's trying to push the beam inside. So that is the sign convention, which is a way to do it. If you are if you are okay with the Cartesian coordinate sign convention, it still follows that as well. So either way, you are still good. So this is how it is. MP is PR. You know what R is, you know what P is, and you know N is. N is simply minus P because force balance, N is minus P. So put everything in this. You know A, you know N, M, Rn, all of that. So you will get a sigma theta theta expression, right? So you'll get sigma theta theta equals N by A, M Rn minus R by AER. So that is minus P by A, PR, sorry, this is small r. What is the small r? It is the radius, right? So you're trying to find out what sigma theta is at a particular r value. So that is this r upon AER. So just substitute all the values. You should get sigma theta theta as, oh, let's see if I've got sigma theta theta somewhere. Okay, sigma theta theta is, oh, actually I haven't calculated for sigma theta theta. See, is it there? Now I guess substitute the values, you should get an expression for sigma theta theta. Substitute set r equals ri, you should get sigma theta theta at A. And substitute r equals r naught, you should get sigma theta theta at B. That's fair. And you can find out what the maximum value of sigma theta theta is now that you know what the distribution is. So multiple ways to do it. You can find the derivative with respect to r. Generally, it's at the extreme, extreme ends generally. So you can look at what's happening and you can figure out where the maximum tangential stress is. That is how you solve this problem. So it's basically finding the tangential stress, find out each of the elements in that formula, and you can get what you want. Yeah, is using Winkler's theory. That's correct. You can use any theory. That's fine. Doesn't really matter. This is more direct in the sense you have a set formula. You just have to, calculate each of the terms and just substitute it. So that's it. Again, if at any part you've been confused, either because of the sign convention or anything else, you can stop by after the discussion, or you can ask me right now, or you can drop by in the office hours if you want to go take a look over it again. But all of that, try to be comfortable with the conventions in the sense